In this video we're going to look at a variation of a functional of this type here. So we've seen this previously where it's a simple functional of x, y, y derivative. Now we're extending it to y double derivative, y triple derivative up to the nth derivative. So the y subscript n just means the nth derivative of y. So what we're going to do initially is we'll simplify it for n equaling 2, so we'll only have the first 4 terms here, and then we'll generalize it up to y equals n. So what we have here is the idea of adding a variation onto a functional. So if you're unsure about this here, there is a video you can click on up here at the moment on the derivation of the Euler-Lagrange equation, which goes through this in detail. But let's have a recap here. So if we had some extremum y of x, that's it in yellow, from the boundary points A to B. By an extremum, I mean, for example, if we had a hanging rope, then the potential energy would be minimized on a hanging rope. So the extremum in that case would be the potential energy. So this is just some random extremum. Now what we want to do is we want to add a variation on that extremum. So we add the variation onto the entire function. So in order to do that, we create another function called eta of x. So that's it in pink there. And then we can multiply that eta of x by some value epsilon. So that's just a number. So that'll give us a family of these curves. And then we add this epsilon to x onto our y of x to get our new function, large y of x. Okay, so large y of x equals y of x plus epsilon eta of x. Then the idea is that we can look at the limit as this epsilon tends towards 0, and as epsilon tends towards 0, this function here, y of x, will tend towards our extremum small y of x. So we notice here a few things, that eta at A is equal to the eta at B, and also the rate of change of eta with respect to x at A and B are all equal to 0. So let's go ahead and we'll take this derivative, dy by d epsilon. So dy by d epsilon, now the large y here is the small y of x plus epsilon eta of x, so we'll pop that in there. Now remember, we differentiate that there. We're going to have one term for this, and we're going to have two terms here because it's a product of two terms. So we differentiate one, multiply it by the other, and then differentiate the first one, multiply it by the second one. Okay, so we'd have d by d epsilon over y of x, and then we'd have d epsilon by d epsilon times eta of x, and then we could have our epsilon, and then we can differentiate the second term. It would be d eta of x by d epsilon. So for these three terms, we'll notice that the first thing here, notice that the y here is a function of x, not a function of epsilon. So when we differentiate that, it's just going to go to 0 because it's not a function of epsilon. The second one is d epsilon by d epsilon is going to give us a value of 1. So we have 1 times our eta of x. Now the third term here is the same as the first term, that eta is not a function of epsilon, it is a function of x. So when we differentiate that, that's just going to go to 0. So all we're going to be left with is our dy by d epsilon is going to equal e to x. So by the same process here, we can also say that when we differentiate the second term, it's going to be dy derivative by d epsilon is going to be eta derivative of x. And also, I never put it in there, but we can say that the dy double derivative by d epsilon is going to be eta double derivative of x. Okay. So what we're going to do then is simplify this out, and we'll write them out in this to make the nomenclature just a little bit simpler. So large y of x we'll write as y, and then the first derivative we'll write as y derivative, the second derivative is y double dash, and again for eta of x is eta, the first derivative will be eta dash, and the second derivative will be eta double dash. So when we look at a small variation in that functional delta I, then what we could do is we could take the new point, okay, the new value of the functional minus the old value of the functional, which is really taking the new value of functional here minus an old value of the functional at that point there. Okay, so whenever we subtract these off, we can then look at this in terms of the first term in an Euler approximation. So sorry, in the Taylor approximation. So that would be epsilon times the differential of this thing here. Okay, so when we differentiate this here, we'll note that we're differentiating it with respect to epsilon. So our function here is a function of y, and then y is also a function of epsilon. And again, a function f here is a function of y derivative, and y derivative, should that there, y derivative is a function of our epsilon, and our third term here. So if we were doing just the Euler-Lagrange derivation for a simple functional, we would stop at that point there and then go and do integration by parts, but we're extending this up to a higher order derivative in y. So the third variation is going to be a partial f by partial y double derivative by dy double derivative by d epsilon. So in effect, you could look at that there as a total differential. The x term of the total differential is not in here because x is not a function of epsilon. So we know that for this to be stationary, we must have this here equaling 0. Okay, so we're going to have all that equaling to 0. So another thing to note, that when we write things like partial f by partial y derivative, in terms of the function, we're actually writing partial f of y derivative by partial y derivative. Okay, so if you're unsure about differentiating of functionals, there's another video up here, which if you click on that just now, you can get through and it will describe to you all the rules for useful rules and identities for differentiating functionals. Now, what we've got to do here is we've got to get the eta out of this bracket, okay, and also we've got to get rid of the eta derivative and eta double derivative. Now, integration by parts, that provides both of those requirements. So what we're going to do is we can leave that one as is, because we can just take the eta out of the bracket. But this thing here, we've got to get rid of the eta derivative. So we use integration by parts, so we'll integrate that second term here by parts. Now, if you're not unsure of integration by parts, there's a video here. If you go and click just now, I'll go through a description of integration by parts. So if we have an integral of two functions, the product of two functions, integral of u dv would be equal u times v minus integral v du. So in this instance here, we can let u equal partial f by partial y derivative and let dv equal our value of eta derivative. So if we were to integrate the integral of dv, we just give us our v, and the eta derivative would just go back to our value of eta. So we'd have our u times v. Well, u here is going to be partial f by partial y derivative. Our v is going to be our eta, and that's over the limits a, b, and take away the integral from a to b of the v du. So v again is just a value of eta. Now the du, so we're differentiating with respect to x, and we're differentiating u with respect to x, which is partial f by partial y derivative. So that's going to be eta d by dx of partial f by partial y derivative. Now we know that eta a equals eta b equals 0. We can see that from our diagram up here. So the value of eta at a and b is equal to 0. So it means that the first part of this term here in integration by parts will go to 0 because eta at a equals eta to b equals 0. So we'd just be left with this part here, minus integral from a to b of eta d by dx partial f by partial y derivative by dx. And you can see here then we've now no longer got a function of eta derivative, we've got a function only of eta, which is what we wanted to do. Now, got to do the same for this term here, but this term here is eta double derivative, so we've got to iterate the integration by parts. So in effect, do integration by parts twice. So when we do the integration by parts twice, now if you're unsure about that, there's a video up here. If you click on it now, I'll go through the integration by parts and the iterative method for doing that. So this is the function here we want to change. So we end up with a eta derivative partial f by partial y double derivative from a to b minus eta d by dx of partial f by partial y double derivative from a to b plus the integral from a to b of eta d by dx partial f by partial y double derivative by dx. Now the first two terms here are going to disappear because eta, as I mentioned before, and eta derivative are equal to 0 at points a and b. So we're left with this factor here. So now what we're going to do is we're going to put the three factors together. So we've got our original term here, eta partial f by partial y derivative, and we've got the new term for this one and a new term for that one. So we'll put them all together and we'll have this term here. Okay, so that you can see then that allows us to then take this value of eta out of the bracket. So that's eta as a function of x. So eta function of x comes out of the brackets. We're left with what's inside the brackets here. Now we know that eta of x doesn't equal 0, and we know the whole thing there has to then equal 0 for an extremum. So we know that epsilon doesn't equal 0, eta x doesn't equal 0. So the thing inside the bracket here must equal 0. Now we use the fundamental lemma to then suggest that to say that this thing here equals 0. So if you're unsure about the fundamental lemma, there's a bracket, there's a video up here. If you click on it, it'll take you through to the derivation of the fundamental lemma of calculus of variation. So the fundamental lemma really just says that if we have one function here and another function here, when we multiply the two together, if we say that one of the function isn't equal to 0, then it means that the second function here must be equal to 0. Now also note here as well that if we take in, if the limit is epsilon tends towards 0, so as epsilon tends towards 0, that large y will tend towards our small y. So you can see that from our original equations up here. If our epsilon tends towards 0, then this y of x, large y of x, will just tend towards that y of x, because this term here will tend towards 0. So it means that we can then get in and rewrite this here, and we've got our final equation here, which in effect is our Euler-Lagrange equation, but for a function with a y-derived, double-derivative term in it as well. So partial f by partial y minus eta d by dx partial f by partial y derivative plus d by dx partial f by partial y double derivative will equal 0. So that's what we've been looking to get. So what we're going to do now is we'll generalise that to the nth derivative case. So when we generalise it, we just rewrite the equation out here. It's going to be partial f by partial y minus d by dx partial f by partial y derivative plus t2 by dx2 partial f by partial y double derivative minus plus minus plus minus plus, so it's minus 1 to the power of n dn by dx to the n partial f by partial yn equals 0. Okay, so that's the final equation that we're looking for, which is our Euler-Lagrange for the nth derivative of y. So now we're going to just note, we're not going to prove it, but we'll look at the conditions for our minimum and maximum, and we're stated it only for the value of n equaling 2. Okay, so it's only for y and y derivative. So the equation 1, which is in the last page, which is the equivalent Euler-Lagrange for a y and y derivative, that must be satisfied, and the conjugate points has to be out with the interval AB. Okay, a little bit more involved than that, but it gives a rough description of what's happening. If you're interested in conjugate points, there's a video up here that'll go over conjugate points. You click there, you can have a little look at it. Now the third thing here then is if partial squared f by partial y2 squared is constant, has a constant sign over that interval AB, then it means that the value of I is a maximum if the sign of this is negative, and the value of I is a minimum if the sign of that there is a positive. Okay, so we've gone through this now, that's finished. It's not a lot of detail in it. I mean, I haven't proven a whole lot of it, but it's meant to be an introductory course, so we don't really need to get into that detail. If you're interested, there's derivative of this section here and the Forsyth books on calculus of variations. I haven't gone over it myself, but I will go over it at some point in time. Okay, so thank you for listening, and I'll get you on the next video. Goodbye.